Today we're going to have a relatively brief recitation session. I'm going to talk about a few things, and then we'll go over the midterm. I think Yungu might make a guest appearance and answer a couple of questions too. So a couple of kind of more administrative things first. One is Oracle is going to be coming to CMU and giving a tech talk next week. I think this is going to be really interesting because they're going to talk about their Spark platform. They're going to talk about their database management systems. They're going to talk about some of their big like data center type appliances. And Oracle is one of those really cool companies where they actually like control the entire stack. So everything from the software that's running on their machines all the way down to the processors is developed in-house at Oracle. So they have this really like broad perspective. I think it could be a really cool place to network with some people. And if you don't have an internship for the summer already, maybe this could be the start of one. So that's going to be next Wednesday, March 27th, and it's from 4:30 to 6:30 p.m. in the Singleton Room, Roberts Engineering Hall. Do you guys know where the Singleton Room is? I mean, it's basically like if you go out this classroom and make a right, it's just down that hall. Okay, that's Oracle. Lab 5. So Lab 5 has been posted. This is going to be a departure from the system Verilog labs that we've been doing. We're going to go back to a functional simulator, and for the remaining labs, you'll be implementing things in that functional simulator. And the labs are only going to get harder from here on out. This lab is going to be relatively difficult. You'll be implementing caching and some main memory operations in the simulator. After that, we're going to kind of come back to branch prediction and stuff, and then we have some cache coherence, which we'll learn about more later on. So again, I can never emphasize this enough, but start really early. And I think the grading is going to be a bit stricter on these remaining labs because we actually give you the exact specification for how many cycles it takes to access the cache, how many cycles it takes to access memory. So you really have to get that timing exact for the program inputs that we'll be giving you. It's not sufficient to just functionally execute the programs and get the right outputs. You're now building the system. You have to get the right timings as well, exactly to the specification. Okay, so any questions on Lab 4? That's due tonight. Though now you have a glut of late days, so you might choose to use those for this lab. Anything? Okay. And Monday, so Monday we might not have class on Monday, just to give you a heads up. We might do a recitation session. We might let you just work on homeworks and labs, which basically means you'll get a break. So I'm not sure what's exactly going on Monday, but just to keep that on your radar. Okay, and without further ado, yeah?
I was going to say, next week then, we'll be covering the caching stuff that we need for the lab.
So we'll begin looking at caching in main memory.
Okay.
Yeah, we'll be looking into that soon. Although I think, having looked at the lab, I think that you have enough information and the lab has enough information within it to help you get started. Yeah. In terms of tuning your actual design, we'll be going over the concepts in more detail in the lectures. Okay. Cool. So, midterm 1. I've asked some of you this in the lab session, but I mean, how was the midterm overall? What are your thoughts on it? It was pretty long, right? It's pretty challenging too, so that's good. That's good. I think people did actually relatively well on the midterm. If you look at how the grades compared to last year, they're relatively on par. And I was really impressed with some of the solutions that you guys came up with for the questions. They were, you did a really good job. I think that there were a lot of questions, but the ones that you attempted and really solved, I think you guys did a good job on that. So I think you're on track for the next midterm, but just keep studying the material, keep asking questions. Yeah. Okay, so the first question, I'm just kind of going to sample a couple of the ones that I think are more interesting to work through, and we can go into more detail on other ones if you want. The first question was that potpourri question. It's pretty straightforward, I think. It's just asking you to sort of analyze different systems or different scenarios. Did anybody have any specific questions on potpourri? Because I'm inclined to just sort of skip that question and go to the more technical questions that we can work out on the board. Because potpourri is just more like question and answer format. But did anybody have specific questions? I know Andrew's looking through his midterm to see if he had any notes. Anything? Okay. So let's actually work through the second question, which is branch prediction and dual path execution. So dual path execution, can somebody remind me what you're actually doing with dual path execution? First of all, what's the high-level goal of branch prediction and dual path execution? What are we trying to do in each of those techniques?
Cycles away for control dependency to resolve.
Yeah, exactly. We're trying to reduce the amount of wasted cycles due to control dependencies. And these are two different techniques that can be employed. Bit of a side note, or let's get back to that side note in a second. So branch prediction, we're pretty familiar with that. You're implementing that in your lab. Dual path execution, we mentioned it in one of the lectures. But what you're basically doing there is you're saying, I'm not going to predict, per se, which way I'm going to take in a branch. I'm just going to go ahead and take both paths. Maybe I have additional hardware to do that. Maybe I alternate between both paths when I'm fetching them. What does that mean? That means that half of the time, or at least some of the time, I'm doing useful work from one of the paths, because I'm going to take one of the paths, and I might have completed some of the work. It might not have been as good as if I perfectly accurately predicted the right path and was only fetching instructions from that direction, but it can be better than getting the prediction wrong or doing nothing at all. So are branch prediction and dual path execution orthogonal to one another? Can you combine these two techniques? How would you combine these two techniques? If we asked you to do that on a future midterm. Any ideas? Yeah?
You could only commit one of the paths after the dependency's been resolved. So you put them in a buffer somewhere, and then when it's resolved, you commit that buffer.
So how does the branch prediction aspect integrate with that idea? So what you kind of described was more like dual path execution, right? You fetch both paths and then you commit one of them after you resolve the branch. But the question is, what about just integrating branch prediction itself? We kind of gave you one idea, though we didn't explore it in too much depth on this midterm, in fact. There's different ways of doing this, but one way of doing it is you could have a separate predictor that just predicts confidence of your branch predictor, for example. You know, the confidence predictor could override the branch predictor's decision and turn on dual path execution if it thinks that there's a particularly difficult branch to predict. And we'll talk about that solution. Others exist. That's just one possible one. OK, so going back to the question itself, the first part is just asking, for a given system design, how much wasted work is there when you mispredict a branch? Anytime you answer some sort of branch prediction question, you need to be able to quantify how much work is wasted on a misprediction. That's key. So here, let's look at the system that we're working with. So what we have is a system with a 7-stage pipeline. I'm going to draw each of the stages here. This is 2A. So we have stage 1, 2, 3, 4, 5, 6, 7. Okay? And branches are resolved in the 6th stage. So how much wasted work is there if there's a branch misprediction? If in the 6th stage we realize that we actually were fetching from the wrong path, how much wasted work is there in terms of number of instructions? You have a 1 in 7 chance of getting it correct. Any ideas? So let's think about it. So whatever's in stage 7 doesn't depend on the outcome of this branch. It doesn't matter which path we took, because this instruction came before the branch, and we know that it was being executed. We know that we need to execute it. This instruction in stage 6 is the branch itself. Is the branch itself wasted work, though? If you realize that you mispredicted on the branch, is that counted as wasted work? It's not counted as wasted work, because that is essentially the question that you're trying to answer, is which direction does this branch go? So this isn't any wasted work. That's good. The instructions in these stages, however, if there's a misprediction, are definitely on the wrong path. And we can't really use them, we can't really commit these instructions because they might modify some state that is incorrect. Are there any cases when these instructions actually could be reused if you were on the wrong path? Do you always have to say all of these instructions are useless? Can you think of any examples where that doesn't necessarily apply?
We're branching over a couple instructions, and this is an instruction from after.
So that's one thing. So what if your branch target was here, and this came after what Andrew's talking about, the hammock? So we kind of draw this diagram for branches. So if we have a branch, and then we have taken, not taken, and we have some code over here, some code over here, and then they join back together at some common location, like if, else, and then the rest of the code. If the size of these sections is relatively small, or the size of the mispredicted section is relatively small, then it could be the case that some of the instructions from after they join back together are actually still in the pipeline. Now, we would also need to make sure that these instructions are independent from any of the instructions that were executed in the correct path that the branch was being taken. But yeah, you can think of a scenario where that would make sense. What if, for some reason, let's say we don't have a very optimized compiler, or this might be difficult to optimize at something like this at runtime. What if there's some instructions that just happen to do the same thing at runtime? What if there's 2 instructions that are basically the same in both of the paths, and those were fetched in the pipeline? Those could potentially be reused as well, their computation. Again, if they're independent from other instructions on the correct path. But anyway, for the purposes of this question, let's assume that, because I believe we say that oh, that's later for dual path execution. But let's assume that the instructions on the wrong path, we just count them as wasted work. We don't do anything special. So if that's the case, then there's actually 5 instructions of wasted work every time we mispredict a branch. OK, so that kind of gives us the building block that we can use to perform the next computations. Now, we didn't mark you wrong if you got this part of the question incorrect. That would be unfair because you have to use, essentially the other sub-questions are dependent on your answer to this part. But anyway, let's start working through the other cases here. So next we ask you to assume that n instructions in a program are on the correct path of the program. So this is kind of, we have magical information that tells us this. And we say, assume a branch predictor that has an accuracy of A. This could be from 0 to 1. And we want you to write the equation for the number of instructions that are fetched on this machine in terms of these two parameters, n and A. And we give you an additional assumption in the beginning of the question, which is 20% of instructions are branches. So with this information, we have what we need to answer the question. This is to B. OK, so total number of instructions that are fetched. So there's going to be two components to this answer. One component is the number of instructions that were fetched on the correct path. The other component is going to be the number of instructions that are fetched on the wrong path. Total fetched instructions equals total fetched on correct path plus total fetched on wrong path. So what we need to do now is figure out how many instructions are fetched on the correct path and on the incorrect path. Well, we gave you the number of instructions that are fetched on the correct path. Let's just write this. Total number instructions fetched OK, so we gave you this number. This is n. We gave you that in the question. And the question then becomes, how many instructions were fetched on the incorrect path? OK, well, let's start here. Before we can begin to think about wasted instructions, instructions on the incorrect path, we need to first figure out how many branches were there in the program. So if there were n instructions on the correct path, remember, branches themselves are by definition on the correct path, and 20% of the instructions are branches, that means that there were this many branches in the program. Now, out of those many branches, how many of them were incorrectly predicted? Well, we gave you the branch predictor accuracy. So that's basically 1, perfectly correct, minus the accuracy of your branch predictor. This will give you the misprediction rate of your branch predictor. And so the combined product of these numbers will give you the number of mispredicted branches. Now the question is, how many instructions were on the incorrect path? Well, for each mispredicted branch, for each one of these, we already found out that we have 5 instructions of wasted work. So we multiply the number of mispredicted branches by 5, and that gives us the number of instructions on the incorrect path, and we can sum these together to get the total number of fetched instructions. Any questions on this? OK, so that's just for regular branch prediction, or that's just for branch prediction. The next thing we wanted you to do was look at the same framework, look at the same system and assumptions, but now replace branch prediction with some other technique that we can use to tolerate these wasted instructions. And the one that we picked was dual path execution. You could imagine having a similar question that does something like, what's another technique that we use to tolerate control dependencies? Wasted instructions due to them. Do you remember another technique? Some ISAs actually employ this technique. I think ARM uses it. Predicated execution. Yeah, we could actually use predication to help alleviate the number of wasted instructions. You could think of another subpart of this question could be, now assume the machine has predicated execution. The average size of consecutive predicate instructions is this long. You could do things like that as well, and you could do the same calculation. Good. But what we chose to look at was dual path execution. So how does dual path execution work? That's the first thing that we need to be able to solve this problem. So the midterm was actually not perfectly clear on what flavor of dual path execution we were using. So the way it was graded was if you used any of the techniques of doing dual path execution, you got credit if you did that computation correctly. So I'm going to talk about two possible techniques, and we'll see why one is better than the other one. So the first possible technique for dual path execution is you could just add more hardware. You could just say, I have fetch. I have like 2 fetch units, 2 decode units, 2 execute units, and then after I figure out which path was correctly taken, I have maybe, register access, write back, something like that. And what you could do is, normally, when you don't have branches, you could just use one of these pipelines. But when you fetch a branch instruction, you could turn on the other pipeline and start fetching from both path directions. And when you execute the branch and figure out what the correct direction was, you could just basically ignore the wrong pipeline. That's one potential way to look at dual path execution. Another you could do is you could do something a little bit more frugally, which is you could keep the same pipeline as before, but what would you do here? We're engineers, right? We can work with these sort of constraints. How would you implement something similar to dual path execution up here, but using just a single pipeline? Let's say this instruction is a branch. We fetch a branch. Now what do? We go to decode. What do we fetch here? We have 2 possible directions. But we have no prediction. So what do? Do we just pick one direction randomly?
You can't take it yet. You haven't resolved the address yet, so you can't take it yet.
Oh, so yeah. So let's assume that in like a nice world, we kind of have these options in front of us. We have very explicit directions that are built into the branch. Basically, these are exactly the directions that we would take. Let's say that we know that in fetch, just to keep it simple. So one option is you could just fetch from a random direction. But if you keep fetching from that random direction, then now you're doing worse than branch prediction because you're basically just making a random, uninformed guess. You're always fetching from one direction, and it's probably going to hurt your performance. What you could do is with this same exact hardware, you could fetch from alternate paths on alternate cycles. So assuming we knew both of the directions, we could pick from, let's call it the taken direction on this cycle. And then the next cycle, when the branch is over here, we could fetch from the not taken path. What does this mean in terms of efficiency? This means that by the time we resolve any branch, we at least have this number of instructions divided by 2 of instructions on the correct path, guaranteed. So this could be another way of implementing dual path execution, which is particularly useful if you really don't know which direction your branch is going to take, but you still want to complete some useful work. So for very hard to predict branches, this is one technique that might be useful, and we'll go into that in the next part of the question. Why would you use one of these over the other? Which one would you rather implement in your processor? It depends. What's something it depends on?
Your area constraints.
Area constraints, cost, basically the same thing. Yeah, this is a much more expensive technique to implement than this technique. Although maybe this is easier to verify than this technique, I don't know. But yeah, that's the general idea, is that dual path execution, this flavor of dual path execution is a little bit less interesting to think about because you're just tacking on more hardware. Now you come across the question of, well, what else could you have been doing with this other hardware? You could have been executing another thread maybe, or maybe there's a different way of writing your program so that you can use more independent instructions like VLIW or superscalar. But with this one, you still get the benefits of the cheap hardware, and you get the benefits of dual path execution. OK, so the solution that I'm going to go over is, let's see, which one should we do? We'll do this one. I think most people actually assumed, most people that attempted this questioning, I think they assumed that this was the execution model, which is perfectly fine. So we'll go over this one, and then I'll explain how you would get the answer to this one. OK, so same thing as before. Total number of instructions fetched is number on the correct path plus number on the incorrect path. So in this case, number on the correct path, that doesn't change. We still have n instructions on the correct path. Good. Number of instructions on the incorrect path. So we first need to know how many branches are there again. We already know what that is. We computed it up there. There's this many branches. Good. And how many instructions do we fetch for each of these branches? How many wasted instructions, I should say, if we're assuming this design. How many?
Whatever your branch penalty is.
Yeah, whatever your branch penalty is. Because if we're at this point and we determine the outcome of a branch, we've fetched 1, 2, 3, 4, 5, 6 instructions. But 3 of these 6 instructions are on the correct path. That's the guarantee of dual path execution. 3 of these instructions, the wasted number of instructions, which in this machine is 3, or I guess this machine is actually 2, yeah, are on the incorrect path. So we would have size of the wasted instructions, which in this same system is still 5. So if you do the computation, 0.2 times 5 is 1. We have n plus n. That's 2n. How does that compare to before? Well, it looks like it's a lot more, right? That's the cost of dual path execution. Why might we be willing to accept this number of fetched instructions, though? What's the benefit that we're getting with dual path execution? What's one potential benefit? Or are we just adding more hardware for the sake of adding more hardware? Probably not. So this gets us performance, right? That's one thing that it could buy us, because when we fetch a branch, now we're guaranteed to have some instructions from the correct path. So we don't have to refetch those instructions and re-execute them. So it's likely that the dual path execution machine could be, for branches that we aren't very confident about, could have better performance than the branch prediction machine. What's a case where this machine could definitely have worse performance than a branch prediction machine? Can you think of an example? What if you're able to perfectly predict the direction of your branches? Is that a case where it could have worse performance? Not really, because even if you could perfectly predict the direction of your branches, you're still only going to be doing as good as the dual path execution machine, because it's already gotten all of the instructions from that direction. But we're making some assumptions about the rest of the system that might not necessarily be true. For example, we're assuming that to fetch this many instructions doesn't incur any penalty compared to fetching something like half as many or less instructions. But in a real system, this might not be the case. In a real system, like with some of the vector machines that we've been talking about, you actually have a limited channel to memory that you can use to request data from the memory devices. Maybe each cycle, you can only fetch one instruction. If that's the case, dual path execution isn't really, this variant of dual path execution isn't really going to help you that much, as much. That's something where branch prediction could actually make better use of the available bandwidth in the system when accessing memory. That's another benefit, in fact, of this flavor of dual path execution. You have the same amount of fetch for each cycle. OK. So another way of looking at all of these schemes is, like I sort of gave a preview of at the beginning of this question, you can actually combine them. They're not techniques that you can just substitute for one another. So how do you combine them? Well, one way of doing that, so let's back up a second. When does the branch predictor perform well versus when does dual path execution perform well? The branch predictor performs well when you're fairly confident that you'll be taking that branch, when you have a high accuracy for predicting that branch. That's like we said, if you have 100% accuracy, then you don't need to worry about dual path execution. Branch prediction is bad when you have a very low accuracy when you're predicting branches, because you're basically making a random guess and filling up your pipeline with half the time completely useless instructions. That's when dual path execution kicks in and actually helps you out, because some of those instructions are guaranteed to be useful. So you could imagine adding a separate level of predictors on top of these schemes whose sole purpose is just to predict how confident am I that the branch predictor is giving me a correct, or is giving me some sort of useful result. So that's a confidence mechanism. We describe it fully in the question, but I just want to sort of give you the high-level sketch for solving this. Basically, we're going back to the same equation from before. Total number of fetched instructions, correct path, incorrect path. Correct path, that still hasn't changed. But now the incorrect path gets a little bit more interesting, because we have two different types of predictions that are going on. And there's two cases when you add a confidence mechanism when you could be fetching instructions on the wrong path. Because now you have two things that are potentially giving you bad decisions. The branch predictor could be giving you mispredictions when the confidence predictor says that it's accurate. And the confidence predictor itself, it's not perfectly accurate either. So there could be cases when your confidence predictor is actually giving you wrong results, which is another case when you'll have wasted instructions. So we can break this down into those two subparts. One is when you have some issues with your confidence predictor, and another is simply basically when you don't have enough confidence to be able to predict that something is being accurate, and you can waste instructions going there. So we'll call this, I think we called this in the solution, this is lack of confidence. And this is incorrect confidence. So lack of confidence, that means that you're going to be fetching additional instructions because basically you're not confident about doing about executing that path, and so you're going to be wasting instructions because you'll switch over to dual path execution. And incorrect confidence, which means, hey, you predicted that something was confident, it actually wasn't, so you wasted instructions there. So for the lack of confidence, we still start out with the number of branches. That's the same as before, and that's similar for both of these techniques. And what happens here is when you have this lack of confidence, that's when you're not confident. We introduce this parameter c, which is basically how often you're confident that your branch predictor is made a correct prediction. 1 minus c is how often you're not confident that the branch predictor is making an accurate prediction. This many times, you're doing dual path execution, and you're wasting a certain number of instructions. So you're wasting that many instructions, like we talked about for dual path execution. Now, for the incorrect confidence prediction, what happens here is this is sort of the dual to this case. So this is when you're not confident. This is when you are confident, but you still make a misprediction, which we define, again, in the problem. We tell you how often this would actually happen, and we called that m. And when that happens, when you're still confident, but you still mispredict, we're going back to the branch predictor part, and you waste that many instructions from fetching from the wrong path. You can basically add those together, and that'll give you the sum. OK? So that's branch prediction and dual path, two techniques for tolerating control flow dependencies. Any questions? OK, cool. So the next problem was data flow. I'm not going to go through this full problem. I think basically this circuit calculated the parity of a number, so it looked at the number of set bits. You can work through that on your own. It's fairly straightforward. You just actually have to try it with several different numbers, inputs, and see the pattern that's coming out and then infer what's going on from there. Similarly, for the mystery instruction question, I'm not going to go through all of that on the board. It's another one of those where you just need to actually go through the steps and step through the execution of the machine yourself. And what that's doing is it's reversing the order of bits of one register and storing it in another register. And we have some pseudocode for what's actually going on there. OK. But I will be talking about the virtual memory question, which is question 5. So in this question, what we were looking at was you have an array. It has a certain size. Its elements are a certain size. And can you figure out, based on how you're traversing this array and based on certain things that you observe in the system, different characteristics of the virtual memory that's being used on the system? So let's take a look at what we're given. We're given that we have a 32K by 8K matrix. So it kind of looks like this. This is how I visualize it. I'm a very visual learner. So 32K rows by 8K columns. And each element in the array is 1 byte. And right now, we're assuming that the elements are stored in row major order. So consecutive addresses correspond to consecutive elements within a row in the machine. Okay? So we give you a couple of different programs. I'll talk about those when we need to reference them. But the first question asks you, if this one particular program that traverses the array in a certain way yields 8K page faults, what's the size of a page in this architecture? Okay, so first, I think there's 2 key things to solving this problem. The first is understanding how does the program traverse this array. So this program, what it's doing is it's going through the rows. And then for each row, the inner loop is going through the rows. The outer loop is going through the columns within the row. Is that right? Inner loop is going through the columns. Outer loop is going through the rows. Yes. So what that means it looks like is it's kind of traversing it in this manner. It'll go all the way down here, and then it'll go like this, and so on. This is kind of how it's traversing the array. Okay. And, yeah?
Wait, are you talking about program 1?
Yes. So, and maybe I wrote this down incorrectly, but it's
you're going to hold the row constant and move across the column, or move across the row, column by column. So if you just look at the inner loop, you're going to be incrementing the column index within a row. So row 0, column 1, column 2, column 3, column 4, row 1, column 0, column 2, column 3.
Yes. Thank you. You're right. So disregard this for the moment. And what Andrew said is completely correct, which is, thank you, which is for program 1, what we're doing is inner loop is going through the columns, outer loop is going through the rows. Okay, so it actually is this sort of traversal. Okay, good. So with this sort of way of traversing the array, what does it mean to trigger a page fault? When does that happen? Without even narrowing down what the size of the page is, let's just think about what's the boundary condition when the page fault would be generated. So let's say we have some sort of arbitrarily sized page that I'm just going to add as a dotted line here. Let's say this is a page size of p. A page fault will occur when we're currently accessing this page of size p, and we want to access something that's outside of this page, basically. Well, for the way that this array is organized and for the way that we're traversing it, we know when that will occur. It won't just be any sort of random access right here. it'll actually happen at the point when we're accessing the last element down here in the array, and we go to access the first element over here in the array as the start of our traversal of the next part of the array. Okay, so that gives us a bit of an indicator about when the page fault will occur. So what we're given is we have 8,000 page faults, basically, 8K page faults. And that means that this transition happens 8K times for this array. So what we need to do is we need to figure out what's the size of this array, and then figure out what's the size of this array divided by 8K. That'll give us the number of these boundaries, which is equal to the page size, that will cause this to happen. So if you go through the calculation, it's 32K times 8K times 1 byte, each of the elements. That's 256 megabytes. And if we take the size of the array and we divide it by the number of page faults that we're expecting to see, we get 32 kilobytes, which is the size that this dotted region, page size p, needs to be in order for us to cross that boundary 8K times for this particular array. Okay. So that's the first part. And the next part says, consider program 2. Program 2 is similar to program 1, with one exception. It traverses the array in a different order. So let's draw our array again. I won't fill in all of the same details. But what program 2 is doing is it's going like this. It's going down. The inner loop is traversing through the different rows. And the outer loop is going through the different columns. Okay, so that's that version. They're kind of connected logically. Okay, and the question is, how many pages should the physical memory be able to store to ensure that this program experiences the same number of page faults as the first program does? Okay. So what's happening here is the program needs to be able to experience 8K page faults. That's basically what we start out with. And that means that given the size of the page, we know that each of these pages needs to only be brought into the memory one time, because there's 8K this many sized pages, and to get the same number of page faults, we need each of them to only be brought in one time. We can't be swapping them out and bringing them back in again. That would give us more than 8K page faults. So what needs to happen is we actually need to have memory that's large enough to hold all of the pages that we'll be working on at the same time. Okay. So if we're traversing the array in this manner, what does that mean? If our page is, I'm going to make it like this. Let's say our memory is just 1 page in size. What's going to happen? We'll access the first element of the first page. We'll access, maybe we can fit a couple of these rows in the same page. We'll access the next element of this page. We'll access the next element of the first row of this page. We'll access some number of those. And then we'll cross over to the next page. What's the problem here? We haven't accessed all of the elements of this first page, but we're already swapping it out of memory, which means that when we get down here and we go to access the second column of the first row in this page, we're going to have to bring the page back in. It's going to give us more page faults than what we're looking for. So we actually need enough pages in physical memory to be able to hold this entire structure. Only then will we be able to, by the time we get to the bottom, have the first page still located in memory. That means we need 256 megabytes of main memory, which translates back to our 8K pages, the number of pages that we have in this array. Okay? So the next question is, again, considering the same program, how many page faults would the program experience if physical memory can only store one page? This is kind of that worst case example that I was just talking about. If we only have enough room to store this one page, how many page faults would there be? Well, we have, basically, there would be a page fault for basically, almost every row, except for, that's not entirely true because we can fit multiple rows into the same page. So if each page could only hold one row, then we would have the number of page faults equal to the number of entries. But each page can in fact hold 4 rows. So we'll have page faults equal to the number of entries divided by 4, because while this page is in memory, we'll access 1, 2, 3, 4 things. Then we'll go on to the next page, swap things out. 1, 2, 3, 4, swap things out. 1, 2, 3, 4, all the way through. So we'll take the total size of our memory, or of our array, 32K times 8K, but we'll divide that by the amount of reuse that we can have within each of these pages. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And what does that come out to? 64 million. OK. That's that one. And if you can store 4K pages, let's say you can't only store just one, but you could store 4K, is that still enough to reduce the number of page faults that you'll have? It's not, right? Because in order to reduce page faults, you would really need to store the entire contents in main memory, like we talked about. So even if you can fit this much of the array in main memory, you're still going to have the same number of page faults. Because by the time you get, no, that's not entirely true, actually. You might be able to reuse some of the pages that you've used before. But, sorry, disregard I mentioned that. But for the case where you can only store 4K pages, it's actually the number where, it's actually this magical sort of halfway point where by the time you reach the end of the array, traversing it through, all of the pages in the bottom half down here would have evicted all of the pages that were brought in the top half up here by the time you go back up to the top. So you'll actually not reduce the number of page faults if you're only able to store a number of pages less than this magical halfway point here. Does that make sense? Kind of messed that up in the beginning. If you were able to store this number of pages, more than that halfway point, you would get some reuse. And the amount of reuse you would have would be this region right here. That size of data would still be in main memory by the time you wrapped back around to this point again, just to clarify that. OK. OK, and basically the next part of the problem, we just kind of switch one of the assumptions and we say, instead of storing it in row major order, what if you stored in column major order, which is kind of like transposing that data. And you can go through and you can work through those examples as well. It's a similar structure to the solutions. OK? Oh, man. So future file. I want to get to the other the branch prediction question, because I think that that's important to understand. Did anybody have questions on the future file? Question from the midterm? Yeah.
How exactly were you able to figure out where the divide occurred?
So the divide. OK, yeah. Let's look at it then. Let's use this one. OK, so let's look at what we know. Valid, exception, which I'm going to abbreviate like that, opcode, one of the registers, destination, source, source, destination value, ready. What we're given is that all of this is the ROB for problem 6. What we're given is that all of the instructions in the ROB are valid. This is the oldest instruction. It was fetched first. This is the youngest. What else did we give you? For this instruction, let's do this. I'm going to get confused otherwise. OK. For this instruction, the destination register was R1. One of the sources was R12. For this instruction, destination was R7. For this instruction, it was R10. The destination value for this instruction was 3. This one's ready. This one's ready. And I think that's it. OK, so I'll work through the solution quickly, and I'll spend more time on how you differentiate between where the divide is actually located. So the way that I think there's lots of different ways of solving this, the way that I personally solve this question is kind of like this. So first of all, we know that I would first focus on these two instructions. They're both valid, and we know that their values are ready. That's a given. This one, we know its destination value is 3, and it's ready. So we can actually look in the register file and see which entry corresponds to 3. That's the one that this instruction stored. So if we look in the register file, we can see that 3 is in R4. That would have been the destination for this instruction. We can fill in one thing here. And we can look at what within the register file would have actually... Sorry, I'm making some assumptions here, and I should probably not do that, and I should back up. I'm just trying to sort of fill this in more quickly than I need to. In fact, you could, I guess, consider that this could be a load, this could be a divide, things like that, right? That could be potentially possible. But what you'll find is if you put a load or a divide in these positions, and you look at other ways of putting in the divide within these two positions, or even this one, both of these instructions wouldn't have had time to finish and write back their result to the register file before this state in the machine was encountered. So if you actually go through and check, what if this was a divide? What if this was, or a load? What if this was a divide? What you'll find is that by the time you reach an exception, even if the exception causing divide was in other places, you wouldn't have had time to write back the results over here. That's because of how long it takes to perform a load, how long it takes to perform a divide. Yeah?
During the test, I asked something like that, and you said that after the exception occurs, everything can continue to proceed as normal.
Everything what?
Continues to proceed as normal. Like we don't say that the exception stops anything.
That's correct.
Then why can't the other stuff just continue?
Because in the question we said that this is the state of the machine immediately after the exception. In the actual machine, it might continue executing. But the state that we gave you, which I also mentioned, was immediately after that exception occurred. So it's an instantaneous point in time. It's not like we kept playing through step by step what happened in the machine. Do you see what I'm saying? It's like a snapshot frozen in time immediately after the exception. Okay? And what I was saying was that the machine eventually could recover from this exception. It's not like it's just halting and there's going to be garbage data in these registers later on. But for the problem that we gave you, this is just a snapshot of what happens right after the exception. Okay? So if you actually go through and you put the different instructions in these slots, you'll find that the only instructions that could have been here that could have written their value already would have been add instructions. So going back to this, well, we still know the destination value was 3. What two registers could have summed to give 3? If you look in the register file, there's an R3 that has the value 0 and an R4 that has the value 3. We could have added those two together to get 3. So I don't know, let's just say I could do R3, R4. OK. So we're given that this instruction, and this is an add, and it couldn't have generated an exception. Good, one down. We're given that this instruction stores its value in R7, and that register is also valid. So we can look at R7, and we can say what value is in there. Well, that value is 17. This wrote back the value. Yeah?
Before that one that you just filled in with the
Yeah.
how can you be certain what the value of R4 was before that add? Because at least when I was taking this exam, I did notice that it's 0 plus 3. But because you wrote the 3, you had no idea what was in R4 beforehand. So it could have been 18, it could have been 27, it could have been anything we don't know. So for that question, there really was no way to get 3 unless you knew that R4 had 3 before it wrote 3 back. If that makes sense. There's no other way to get 3 except to add, well, at least using an add instruction and counting other instructions, besides adding the R3 and R4, except R4 was written to. So what was in R4 beforehand, what it used as the add is an indeterminate value. It can't be known to be 3.
But are there any other, so I guess the question is, are there any other values that it could have been that when summed with any of the other values in the register file would have given you 3?
It could have been R7 actually, would have also, I didn't write that down because I was rushed with other things, but it could potentially be R7 because R7 was also written over.
But it was written over later, right?
Right, but you don't know what happened in the first. So as in R7 could have had 3, let's say. Then at this point in the machine, when we see the future file and when we're filling out the reorder buffer, we'll see R7 17 because as we see its data values ready. We had to go through and actually figure out that the only things that could have been added it would have been 17. But what that was previously, when we were fetching the add instruction, could have been anything, could have been 3. And by that point, we would have hit, eventually, it would have been written over to be 17. And what we're looking at now says 17. So
yeah, that's a good point. Let me actually.
It's a little bit ambiguous. It's just what I'm saying is that it could be multiple things.
I'm going to go back and check and make sure that it's only one thing. If it's not, then we can adjust things accordingly. Yeah.
But that's what I'm just saying. I think it can be multiple things because because we're suggesting it has to take its own value, or it has to take a value from a register that was written over. There's no 2 values in this that we can know that haven't changed that add up to 3.
So you're saying it could have either been R7 as well?
Yeah, based on just looking over it now,
okay.
It looks like it could also be R7.
I'll go back through that again and check and see what the status of that is. And like I said, we can adjust things if we need to. Good. Thanks for pointing that out. Then. Okay, so I'm going to put a question mark here. This might be also R7. Okay, so going back to the other instruction, now we're looking at what's stored in R7 here. It wrote the value 17 over the old contents. That's valid. So we can do something similar. We can look at what values could have summed to 17 by the time that this instruction was read in the pipeline, by the time the instruction read those registers. So for example, R8 and R9. You can sum 8 and 9. That gives you 17. So we can fill that in here. OK. And like we talked about before, this is an add instruction. It won't generate. Now, this is when we get to the part where we're looking at where does the divide go. There's two potential places where the exception causing divide could have gone, here or here. So let's write down what we know about what happened in this machine so far. We know that at some point in time, the pipeline looks like this for the adds. What's our assumption? There's a 4-stage pipeline. Fetch and decode take 1 cycle, write back is 2 cycles. So an add would look like this. Fetch, decode, add takes 1 cycle. So it would take 1 cycle to execute, and it would take 2 cycles to write back. So this is what the first add instruction would look like. The next add instruction, which was fetched after that one, would look like this. Similar, fetch, decode, execute, write back, write back. This much we know. The question is, where could the divide have gone? So let's just pick one place. Let's put the divide right here. Maybe it was there. So what would have happened in the pipeline in this case, would be we would have fetched the divide, would have decoded it, and let's see, what do divides, how do those look in the machine? So a divide takes 3 cycles to execute, and a divide by 0 exception would be detected during the 2nd cycle. So if this divide generated the exception, then we would have something like fetch, decode, execute, things are going okay. Execute, uh-oh, we have an exception. If this were the divide that caused the exception. What does that mean? That means that this would have been the state, everything here, would have been the state that would have been present in the reorder buffer by the time we got to this point in the program. But this can't be the state, because we know that the 2 add instructions already wrote their value back to the register file. This is a bit too early. We couldn't have executed the divide that causes the exception here because we just couldn't have had time to execute the adds that eventually write back to the register file. So we can rule that out as an option. Let's try putting the divide in the other location. Let's see how things work out there. Roll back time. OK, so if we put the divide here, is this a divide? We would have fetched it right here, decoded it. We would have executed the first stage of the divider. OK, things are going fine. We would have executed the 2nd stage, and at the end of this stage, uh-oh, we would have had an exception. What would the state of the reorder buffer have been? Well, it would have been everything that happened before this point in time. Well, this is consistent with what we have so far, because both of the adds have had a chance to finish their write back stage, and they've written back their values. The divide still caused the exception, stopped the machine exactly at that state. OK, so this is where the divide that caused the exception could have been. It's not a question anymore. What does that mean for the reorder buffer? Well, this instruction caused an exception. Furthermore, it was a divide. Its destination value certainly wouldn't be ready, and we don't really know what it would have been, or what the contents currently is stored in the reorder buffer. It's just an unknown. The way this was graded, by the way, is if you have a 0 here, you can put anything here. That's fine. So the question is, what caused this division by 0 error? Well, we know that this source operand had to have been 0. That's the only way we could get the division by 0 error. And we could inspect the contents of the machine and just look at, OK, what could it have sourced in order to have divided by 0? Well, the only register that has 0 in it is R3. and we know the contents of the other registers that might have been updated since the divide was fetched. What was it dividing by 0 with? Well, it really could have been anything, in fact. So as long as you got this right, you could put anything here. It's perfectly valid. OK, that leaves, is everybody OK up until this point? Except for the thing that I'm going to get back to you on Mike. OK, so the next question is, what could have gone here? What instruction could have gone here? So for this instruction to still be in the reorder buffer, let's take a look at what this instruction could have been. Remember, it's still in the reorder buffer and it's valid. What if it was an add? Let's start there. Never mind what registers it would have sourced. What if it was just an add and everything else worked out OK? We would have fetched the add, we would have decoded it, we would have executed it, write back, write back. After this point in time, after this write back, what happens? We can commit the state. We're basically done with this instruction. So if this instruction were an add, at this point in time, 2 cycles after it wrote back its result, it would have actually not been in the machine anymore. It wouldn't have been valid to begin with. So what this tells us is we need to find an instruction that would have still been executing at this point in time in the program. Let's put that back to valid. Another option is a divide. You could have a divide that doesn't generate an exception. Let's look at that. So if we had a divide here, we'd have fetched it, decoded it, execute, 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 write back, write back. What does that mean? That means that it would have written its result back to the register file. And it would have been removed from the ROB the next cycle. Well, if it, let's see, so what could have possibly happened here? Could that state, is that state actually possible? Could you have put that divide right there? I don't know, let's look. What's R1? R1 is 21. So we would have needed to divide R12 by some value to get 21. What's R12? 19. This isn't looking very hopeful, right? It turns out there aren't any registers that you could have used to generate this value that's stored in the destination. So it looks like this divide actually couldn't have been executed on this machine, functionally speaking. OK, so we've eliminated the divide by inspecting the contents of the register file. That leaves us only one option, which is a load instruction. If we had a load here, what does that mean? We would have fetched the load, decoded it. How long does load take to execute? It takes 5 cycles to execute. 1, 2, 3, 4, 5. It would have just finished executing but not written its result back to the register file yet at this point in time in the machine. So this could be a plausible option, right? If this was, loads don't generate exceptions. If this was a load, and it just simply hadn't written its value back to the register file, we wouldn't have known what that value was yet. The question is, that's where it's going to store the value it'll load. And the value that it will access from main memory and store into this register, the way we've specified it, is the sum of the contents of this register and this register, like a base and an offset. So what's the offset? The offset is 19. Okay, so we have some address, and we're adding 19 to that to generate our target address that we want to load from in memory. This is like the address space. Are there any constraints on the way that we can access main memory? Well, we can look back into the problem, and we can see that the calculated memory address, this one, is guaranteed by the compiler or programmer, for example, to be 4-byte aligned. That means that it needs to be aligned on 32-bit increments, and the memory is bit addressable. So it needs to be aligned on 32-bit increments, and it needs to be addressable at that bit granularity. That means that a load address has to be a multiple of what? It has to be a multiple of 32 in order for this memory address to actually be valid, to receive memory from that location. So that narrows down our search a bit. Now we just need to worry about what plus 19 equals some multiple of 32. The first thing to do would be, since we have a list of numbers that we can choose from, we can just look through the register file. And it turns out that R2, 13, you can add that to 19. That gives you 32 exactly. That would be a valid memory address that we could load from. So we can fill this in with R2. OK. And with the exception of this register, which I'll go back, I'll look at the problem again and see, could this actually have occurred? This would be the state of the reorder buffer at the point in time right after the divides exception was detected. Of course, you could have reversed these. That's possible. And since these are unknowns, really anything could be placed there. Unless, of course, you don't make the proper assumptions, like you say that this is valid, but then you place within this correct state, those could be different possible register choices. OK. Any questions? OK. Branch prediction. So with that, I'll turn it over to Yungu, who will talk about branch prediction.
OK, then I'll now talk about questions 7 and 8. There are actually two parts to the same question, so I'll solve them together. So let's see. I'll erase this. So this question first starts off with asking high-level. OK, so the source code that the questions deal with has to do with a for loop, which has 3 if statements embedded inside of it. And so the for loop is iterating through a very, very large array. And this array is known to be pre-populated with completely random positive values. And these are not pseudo-random, but truly random positive values. And as the for loop iterates through each element in the array, what it does is it checks the elements against 3 tests. So first of all, it checks whether it's a multiple of 2, and then it checks whether it's a multiple of 3, and lastly, it checks whether it's a multiple of 6. And depending on whether the test criteria evaluates to be true, it adds the value, the element, to a sum that it's continuously incrementing. So the notation that we adopt in this question for 7 and 8 is that a branch is defined to be taken when you are executing its fall-through path. So what this means is that if you're in the bracket that corresponds to an if statement or a for statement, then you are actually on the taken path. So given this, the first question, part A of question 7 asks, of the 4 branches, list all those that exhibit local correlation, if any. And so the question is, what does it mean to be locally correlated? And we talked about this in class when we talked about local branch predictors and global branch predictors. And local correlation refers to when a branch statement at a particular PC, the outcome of it is correlated with the outcome of the branches at the same PC that comes after it or before it. So, which means that a particular if statement is, the outcome of a particular if statement or a for statement is, it has correlation with its past and its future. So it talks about temporal correlation about me, about myself. So given that, in this question, only the first branch, branch 1, which corresponds to the for loop, has any kind of local correlation, because the for loop iterates through a very large array, and since assuming that the array is very large, we almost never exit from it. The branch is always taken, so you can kind of assume that the branch corresponding to the for loop is always taken, so it's correlated across time. On the other hand, the other 3 branches, B2, B3, and B4, which correspond to modulo 2, modulo 3, and modulo 6 tests, are not locally correlated because, like we said in the assumption, all the elements in the array are completely random. So given that a particular element happens to be a multiple of 2, in the current iteration of the loop, that tells us nothing about whether the next element in the array will be a multiple of 2 in the next iteration, because it's like looking at consecutive rules of a die. They don't have any correlation at all. So moving on to part B, now the question asks, which of the 4 branches are globally correlated, if any? So global correlation, as opposed to local correlation, refers to when your outcome depends on the outcomes of branches that came before you at different PCs in time. So you can think of it as spatial correlation. And in this case, we can rule out any correlation. So B1 is, we assume that it just kind of goes on forever and ever. So it does not have any correlation to anything. On the other hand, then if you look at B2, then B2 is also not correlated to B1 because B1 is always taken, and if something's always taken, it's not correlated with anything else, right? So between B2, branch 2 and branch 3, which asks whether if there's a correlation between when a number being a modulo of 2 and a modulo of 3, that also doesn't have any correlation because 2 and 3 are relatively prime. So for example, given that a number is an even number, does that have any bearing on whether that number is a multiple of 3 or not? Does it affect in any way whether that number is a multiple of 3? No, because what happens is, so without any prior information, the probability of a random number being a multiple of 3 is 1 out of 3, correct? Given that the number is a multiple of 2, then let's look at all the even numbers, like 2, 4, 6, 8, 10, 12, 14, 15, 14, 16, and so on and so forth. Among those even numbers, you see that 2, 4, 6, multiple of 3, 8, 10, 12. 12 is a multiple of 3. So you can see that every third even number is a multiple of 3. So given that you know a number is a multiple of 2, it really doesn't affect whether that number, it doesn't give you any additional information, affect any way whether that number is a multiple of 3. So branch 2 and branch 3 are not correlated. On the other hand, the important thing in this question is branch 4. Branch 4 is a test for checking to see whether a number is a multiple of 6. And this is correlated to B2 and B3 because if a number happens to be a multiple of both 2 and 3, then it means it's an arithmetic identity that the number has to be a multiple of 6. And this is because 6 is a common multiple of the least common multiple of 2 and 3. So the answer was that B4 is correlated with B2 and B3. So now we move on to part 6, where we asked you to imagine a particular global branch predictor and to fill out its pattern history table entry, only one of them, as the global branch predictor goes through this loop 120 times. And so the design parameters of the global branch predictor are as follows. So the global branch predictor has a 2-bit global history register, which keeps track of the outcome of the last 2 branches it saw, and also a pattern history table, a global pattern history table, which has 4 entries. And this global pattern history table must have 4 entries because the global history register has 2 bits. The number of entries, so since every entry in the pattern history table has to correspond to a value, any possible value in the global history register, so you can see that so the number of possible values in the global history register is 4 because it has 2 bits. So that means that the pattern history table also has to have 4 entries. And each pattern history table entry, usually we talked about 2-bit saturating counters within each pattern history table entry, but in this case, we gave you a very large saturating counter, 11 bits. And this was to ease the way you solve the problem. And as an initial condition, before the code is run, we assume that all the pattern history table entries are initialized to 0. As the code is being run, the counter in the pattern history table entry is incremented by 1 whenever a branch that corresponds to the PHT is taken, whereas it is decremented whenever a branch is not taken. So in part 4 of the 7th question, we ask, after 120 iterations of the loop, calculate the expected value that's stored in the first entry in the pattern history table. So let's walk through this problem a little. So what we're asking is basically this. This is the global history register. This is bit 0, bit 1. This is bit 0. And this bit here corresponds to the outcome of the older branch that it saw. And this corresponds to the younger branch it saw. And we're asking, when these are both taken, this would correspond to a particular entry within the pattern history table. This is the pattern history table. It would have 4 entries. This would correspond to 1, 1, which is taken. And this would correspond to Tn 1, 0, 0, 1, and 0, 0. But in this question only, we are talking about what would be the value stored here. This is an 11-bit counter. After having gone through 120 iterations of the loop. And so this is, given that you've solved the first part of the question correctly, that asks you about local and global correlation, this boiled down to a probability problem, if you think about it. So first of all, what we need to do is break this down into multiple cases. So let's break them down into B3, B4, B1, and B2. Okay, so as you go through the loop iterations, you're going to, I'm going to put this, clip this in a better way, hopefully. Just falling off. Okay. So as you go through different iterations of the loop, different branches, each of the branches have a chance to contribute. And by contribute, I mean incrementing or decrementing this particular pattern history table entry. So, so what we're going to do is, so B3 might actually have a chance to increment, decrement the PHTE. B4, B1, and B2 as well. So first of all, let's take a look at, so So in order for B3 to be able to actually increment or decrement the pattern history table, it means that the B1 and the B2 that came before it had to be both taken, right? And if this is, and whether this is taken or not taken, this would increment the counter, whereas this would decrement the counter. So what we need to do is, for a given instance of the third branch, what is the probability that B1 and B2 that came before it were actually taken? So for the purpose of this example, the probability that the first branch was actually taken is 100%. And that's because we're iterating through a very large loop. So the probability of the first branch being taken is 100%. And the probability of the second branch being taken is 50%, because branch 2 asks whether a particular element is a multiple of 2 or not. So the probability of having 1, 1 when we actually get to branch 3 is, if you multiply the 2, is 50% for a given iteration. Now, given this conditional probability, conditioned based on the fact that B1 and B2 are both taken, what is the probability that B3 is actually taken? If B3 is taken, that means that the number is a multiple of 3. And that happens with 33% probability. And this is easy to, because there's 1/3 chance that the number is a multiple of 3. On the other hand, the probability that the branch is not taken is 66%, because they have to add up to 1. So for B3 at least, what we see that is for a given iteration of a loop, the probability that B3 will increment the first pattern history table entry is 50% times 33%. It's the probability of incrementing, whereas the probability of decrementing is 50% times 66%. And if you, so this is the probability incrementing, this probability decrementing. So if you actually add these two up, then you see that the probability, the net effect that branch 3 has on the first pattern table PHT entry is 50% times 33% negative for a single iteration. But since we're going through 120 iterations, we need to multiply this by 120 to get the net contribution of that B3 would have on the first pattern history table entry. And if you multiply this by 120, what you get is, since this is 1/2, 1/3, if you get this, since it comes out to 1/6, this comes out to be -20. So over 120 iterations, branch 3, on average, will decrement the first entry by 20. And you can go through these steps for the other branches as well. And we'll do this really quickly. So now let's take a look at branch 4's contribution. So for branch 4, so first of all, we need to look at the probability that B1 and B2 and B3 were taken before branch 4. And that would be, let's see, B2 and B3. So what is the probability that B2 and B3 are both taken before B4? This would B2 would be 50% as usual, because it's checking for an even number. Wait, did I do this correctly? Yes, okay, B3, okay. And B3 is 33%, because it's checking for whether if this number is a multiple of 3. And if they're both taken, the good thing is that B4 is 100% always taken, because B4 is checking to see whether a number is a multiple of 6. And given this two information, then that number always has to come out to be a multiple of 6. So branch 4 always increments, and it increments with probability 50% times 33%. And since this happens over 120 iterations, you have to multiply this probability by 120. So this was the net contribution from B3. And if we calculate the net contribution from B4, then B4's contribution is equal to 50% times 33% times 120, because it never decrements, only increments. And this comes out to be 20. So this is B4's contribution. Okay? And you can see that these two cancel out right now. So the expected value of the first PHT entry is 0 at this point. But now we have to move on. We have to evaluate the other two. So now let's take a look at B1. In order for B1 to actually contribute to the first pattern PHT entry, it means that B3 and B4 are both taken. So, okay, so assuming, okay, so given that these are both, so what is the probability of them both being taken? So this is asking, this is B1 corresponds to the for loop branch, and B3 and B4 were tests. We're testing whether the previous element in the array were actually multiples of 3 or 6. And this probability is 33. Well, so given that since you already know that B4 is a multiple of, so the probability of a number being a multiple of 6 is 1 over 6, right? 16.6%. And given that it is a multiple of 6, well, I mean, it had to be a multiple of 3 to begin with, right? So the probability here is 16. If you multiply these two, then the net probability is 16.6. And B1, again, for our purposes, is always taken because it's the for loop branch. So the B1's contribution, B1's contribution to, okay, let's write it here. B1's contribution is equal to 16.6% times 120, which comes out to 20. So now let's look at the last branch, B2. And this would require that B4 and B1 are both taken. And we know that B1 is always taken with 100% probability because it's the for loop branch, which iterates to a large array. And B4 is a probability that the element before it was a multiple of 6, which is 16.6%, 1 over 6. And so given this information, what is the probability that B2 will increment or decrement the particular entry in the pattern history table? It's actually split both ways, right? Because B2 is testing whether a number is a multiple of 2. So the branch out can easily go either taken or not taken, which means that, so since this increments with probability 50% and decrements with 50% probability, the net effect is that this actually does not contribute. B2 does not actually contribute to the first pattern table entry. So B2's contribution is actually 0 because it's split equally in both directions. So if you add all these 4 contributions up, minus 20, 20, 20, and 0, then you can see that the expected value within the first pattern history table entry is 20. So this was the answer for part 3 actually, of question 7. And the bonus question, question 8 in the exam, the first part of it actually asks you to fill out the rest of the entries here. Here, here, and here. So filling out these other entries is equivalent to the steps we've taken here. So I mean, it looks kind of daunting, the amount of calculations that we did, but it's actually not that. So this is because I went through it in detail, step by step. This is actually easy to solve if you draw a probability diagram. So for example, one way you can solve this problem is by starting with B1, B2, B3, and B4. and drawing different ways in which the branch out can be resolved. So for B1, we know that it's always taken, right? So there is no not taken path. So we can immediately eliminate this path. At B2, since we're testing whether it's taken or not taken, so the outcome of taken is 50% here, and not taken path after B2 is 50% as well. And then you arrive at B3, which can also go in a not taken direction with 33%, 66%. And arrive at B4. These are B4 instances. And assuming that, so B4 is only taken for this path. This is the only time it's taken. The other time it's not taken at all. So these are all not takens, not takens, not takens, not takens. So if you draw this probability diagram, calculating the pattern history table entry just comes down to looking at different instances. So for example, what we did before was look at TT and look at this guy, TT and look at this guy, and looked at TT and look at this guy. And we wrapped around. So now for the other pattern table entries, what you need to do is find cases when it's, for example, if you're trying to calculate the value for this pattern history table entry, you need to find all the instances where it's taken, not taken, which corresponds to taken, not taken, taken, not taken here, and taken, not taken, and I think that's it. Taken, not taken wouldn't be valid here because it's always taken. So yeah, if you draw this probability diagram and go through different steps, you can actually calculate all the other instances pretty easily. So I won't actually go through the steps here. And the second question asks, given that you have populated all the pattern history table entries, it asks you the accuracy of the global branch predictor when it's iterating through a billion iterations. So once you have this pattern history table filled up, then it's actually pretty easy to calculate the accuracy because okay. So solving this problem also involves splitting the cases into 4 categories. So you would first start off with, given that the current branch history is TT. So for example, so what you need to do is, so after you filled in these 4 table entries, you would first need to look at whether they're positive or negative. So if a value in the entry is positive, then it means that for every single branch in the iteration, whenever it sees TT, if this is 20, the branch predictor always predicts it as being taken. So for example, if the second entry happens to be minus 20, for example, then it means that the branch predictor always predicts the branch as being not taken if it sees a global history of 1 and 0, and so on and so forth. So what you need to do is, given this information, go through each of the instances and see, okay, so given that, for example, let's see, this is taken and taken, my branch predictor tells me that if I see a taken and taken, I should always predict as it being taken. But it turns out to be the case that for other cases, it might not actually be not taken. It might actually be not taken. So you have to factor this in, look at this branch tree, probability tree, and tie it in with the history table and calculate the accuracy of your predictor. So yeah, so that was mostly a calculation problem. And so the last part of the bonus question asks a more high-level question without being bogged down with the implementations. So it asks, without prior knowledge of the contents of the array, what is the highest accuracy that any type of branch predictor can achieve during 1 billion iterations? And this number is actually, this calculation is actually pretty easy because we saw that the 4 branches, B1, B2, and B3, and B4, so the 4 branches were B1, B2, B3 and B4. So without any information about the array, then so B1 is always taken because we're iterating through a very large loop. So a branch predictor can potentially predict this with 100% accuracy, close to 100% accuracy. For B2, since this is checking whether a number is a multiple of 2, then the best that a predictor can do is 50%. It can only get 50% of the outcomes correct because it's completely random by definition. The same goes here for branch 3, where there's 33% of a branch predictor actually having the correct accuracy. And for B4, it's you can actually get this correct with 100% probability because given that you've seen the outcomes of the first 2 branches, and the branch predictor can say, oh, the first 2 branches came out to be true, taken. So I must, the 4th branch must also be taken because of global correlation. So this is the maximum theoretical possible accuracy that you can achieve. And if you average these numbers, then you get, if you average these numbers, you get 71%, which is the maximum possible theoretical accuracy that any branch predictor can achieve. So that was a review of questions in the exam, and I'll hand it over to Jason. Justin. Sorry.
It's okay. You only work with me, so. That's pretty much it, you guys. I just wanted to tell you have a really good weekend. Get started on Lab 5, and if you have any questions, come see us in office hours or labs. Take care.